So good evening, and welcome to the latest installment of the SLAC Public Lectures. Today we are very pleased to have Dr. Brian Lantz of Stanford University to come and talk to us about the discovery of gravitational waves by the LIGO experiment. Dr. Lantz has been intimately involved with this effort. Many years ago, as an undergraduate at MIT, he went to work for Dr. Ray Weiss, one of the original inventors of the technique used to do the LIGO experiment. He went there, I guess, during the year as an undergraduate, and he just got sucked into it. He stayed at MIT to do his PhD. In his PhD, he did an experiment that, what shall I say? For those of you who know about laser measurement, set the world record for the tiniest fraction of a fringe that one could observe in a laser measurement of the kind that he will describe to you in this lecture. Well, with that kind of a pedigree, he then came out here to Stanford, to the lab of Professor Bob Beyer, where he became the leader of the effort involved in vibrational isolation of these extremely precise detectors that are used in LIGO. And so today he'll talk to us about the discovery of gravitational waves and what kind of technology you use and how you pull this off. So Brian, thank you very much.
Great, thank you, Michael. Is my mic on? There we go, good. Well, it's really a great pleasure to be here. It's great for SLAC to host these events. I see there's quite the audience out there, including a couple of faces I recognize. In fact, I see a couple of folks from Mr. Who's 8th grade science class. They're studying gravity right now. I'm going to try to keep the explanations tonight as clear as I can, but if you don't understand anything, get those guys to explain it to you after the lecture. So, as Michael said, I'm Brian Lantz, here to tell you about gravitational waves, the sound that you get when two black holes collide. I'm speaking on behalf of the entire LIGO scientific collaboration and the Virgo collaboration. It's about 1,000 of my closest friends. There we go. You can see the folks who are, this is a list of the people in the LIGO scientific collaboration. I should say LIGO is the Laser Interferometer Gravitational-wave Observatory. And I'll be telling you about laser interferometers and about observing gravitational waves tonight. So there's a list of some of the folks in the LIGO scientific collaboration. You can see Stanford's over here on the corner. And we had a little extra shout out for the locals. We run a network of detectors. The two US detectors for the LIGO sites are at Hanford, Washington and Livingston, Louisiana. The Virgo collaboration is bringing a detector online this fall near Pisa, Italy. The Germans and the Scots, the folks from the UK, have a 600-meter detector in northern Germany. The Japanese are building one underground. The Australians have the corner station of a detector in Australia. And recently, the LIGO collaboration has entered a collaborative agreement with the government of India to build a third LIGO facility in India, which should be coming online in 2022 or 2023. On September 14th, at these two sites, at the Hanford site and the Livingston site, we actually saw some signals that came from outer space that looked like this. I'll tell you more about what strain means and exactly how to interpret these signals as we go on through the talk. I just wanted to show you this right at the beginning. Here's some noise. You're not really seeing anything. And then you see this big ripple at Hanford. And 7 milliseconds earlier, in fact, you saw the same ripple at the Livingston Observatory. And when you line these two things up, what you see is noise here and noise here, but a coincident signal at those two detectors. 7 milliseconds apart. If you shone a light beam directly from Livingston up to Hanford, it'd take 10 milliseconds for that beam to get there. The fact that these arrived 7 milliseconds apart means that instead of the signal coming in to Livingston and then to Hanford, it kind of came in at an angle. So you can kind of tell where that signal is in space, sort of a ring. If you had 3 detectors, instead of doing, as a WAG recently called it, biangulation, with 3 you could actually do triangulation and figure out where the source was. So we're looking forward to some more of these sites coming online this fall and over the next several years. So what did we think caused those signals? Let me just show you this. We'll talk a little bit more about it as we go through the evening. Here are 2 black holes. They're sitting in front of a starry sky, and this black hole and this black hole are each about 30 times the mass of the sun. They're so dense that not even light can get out of the gravitational well. They're about 400 kilometers, about 300 miles across, and the edge of this is called the event horizon. That's sort of the classic edge of that black hole that tells you how big it is. Light can't get past there. And what you're going to see is that as these 2 guys go around, the starry field behind them is going to get distorted. So here they are, they're spinning around. You can see the starry night behind them is getting distorted because the light that you're seeing from those stars is getting distorted as it goes past those 2 black holes. They're spinning in closer and closer together. They're emitting gravitational waves. You can see that the stars, even out here, are getting distorted. And in a moment, this is going to slow down, and you can watch those 2 black holes become a single black hole, and the whole background is getting distorted as the waves go out. This is a really pretty picture. I'll show you a little more technical version now. Here again, we've got the 2 black holes. This blue space is sort of a cut through space-time. And the colors represent time slowing down near the black hole. We'll start those 2 things orbiting around each other. It's just 2 objects just spinning around in space. As they're spinning around, they're emitting gravitational waves. Right now, we're about not quite half a second before these 2 black holes are going to crash into each other. You can see that space is getting distorted, time is slowing down. If you look into these holes, sometimes you can see a little black ring in the bottom as you see the event horizon here. You see time is getting dramatically slowed down. The little colors talk about the direction that space is getting curved in. Here's our waveform coming in. This is about where we could start seeing that waveform in our detector. In just a moment, the thing is going to slow down. And now you see that space, instead of being just rather curved near the black holes, it's getting really distorted and twisted up. And right there, they form a single black hole. And then it ripples down to a single round black hole in just a fraction of a second. That whole simulation was just over half a second. And now you can see those gravitational waves coming out. All right, there's a couple of pretty pictures. Let me tell you a little bit more about sort of what's going on with gravitational waves. Now, usually when people think about gravity, they think about Newton, right? So here's our friend Isaac Newton. And he wrote down this nice formula, the only formula I think that you're going to see tonight, about the force of gravity being proportional to the gravitational constant, the mass of the 2 objects, and the distance between them. So you've got some Earth, you've got some apple in orbit around the Earth. Space is like a big empty stage. You've got these 2 objects, and they're pulling on each other with a gravitational force. It does a great job of explaining lots of things about the orbits of planets, things falling onto the ground. But it has a couple of problems. One of them is that it implies that there's action at a distance. If you have an object here, your apple, and your Earth over here, and you suddenly were to move your apple, if you believed this equation about force, it would tell you that all across the universe, the force of the gravitation from that apple would change instantaneously. And you know that's just got to be wrong. It's puzzled people for a long time. It was resolved by Albert Einstein in 1916 when he said that, in fact, general relativity is the better way to describe what's happening. And instead of space being an empty stage in which you've got these masses, what it says is that space is actually like a fabric. And that fabric is distorted by the mass. And the distortion in that fabric tells the mass how to move. As Wheeler said, space-time tells matter how to move, and mass tells space-time how to curve. And so you get these curved pieces of space around your massive objects. So you've got your sun and your Earth here, and space is getting distorted a lot by the sun and a little bit by the Earth. And they're traveling wave, and you can describe the distortions in this space with a traveling wave if things are suddenly moving around. I'm not going to try and write those equations down for you. We'll do sort of a simplified version instead, right? So if you've got an electron, right, it's got an electric field. If you move the electron, you get distortions in that electric field. And if you accelerate your electron back and forth, you get traveling electromagnetic distortions, or light. And those waves travel out at the speed of light. They are light, either visible light, or radio waves, or gamma rays. If you've got a chunk of matter, it's got a gravitational field. If you suddenly move the chunk of matter, you get distortions in that gravitational field. And those distortions travel out at the speed of light. They carry the information about the gravitational field out to the rest of the universe. Let's take another look real quick at our cool video here. So here you see space getting curved. Here you see space getting very curved. I want you to watch some of the colors in here. You can see these ripples here in the space-time. As our two objects form into a single black hole, if you watch the colors out here, what you'll see is these distortions are going to travel out, and you get little funny color distortions as those ripples, as those perturbations in space-time travel out at the speed of light. I could watch this video all day. I do sometimes. That's not good. So when those waves get to us, they're much weaker. And the way that they interact with us is if you've got some pair of black holes and they're emitting a gravitational wave, when it comes out to here, if you imagine you've got a ring of free particles in space, as the wave comes through, that ring gets distorted into an ellipse, oscillates back and forth as the space-time is getting distorted. So someone in the back row here were to suddenly become a pair of black holes and collide, the waves would come up towards me, and I would get stretched this way and shrunk this way, kind of oscillate back and forth like this as those waves go past, right? That's called the stick man, doing the stick man. So the way we try to measure that is you put a couple of objects in space, and you measure the distance between them with a laser. So here we have a version of the LIGO interferometer. There's a laser that comes in here. There's a beam splitter. There are these two long arms, and you measure with your laser the distance of this arm and the distance of that arm. And as the wave goes past, it's going to distort those distances. And you measure that distortion with your laser. Now, why haven't we done it until recently? Because space doesn't distort very much, right? Space-time does not like to get distorted. Space-time is very stiff. So even if you put a lot of energy into stretching space-time, you don't stretch it very much. The gravitational waves that I showed you before took space-time and stretched it by 1 part in 10 to the 21. We have the world's best strain meter here. We can measure a distortion of 1 part in 10 to the 21 with these long arms. It's not so easy to do, and that's why it's taken us so long, right? Einstein predicted these waves back in 1916. When he did, most people figured you would never be able to see them. There's been a lot of technology advance since then, and we've just now been able to do it. Ray Weiss, who was talking about it earlier this evening, in 1973 wrote a paper where he showed that using these new laser measurement systems, you should be able to finally build a machine that was good enough to do it. And now, what's that, more than 40 years later, we finally managed to do it. I should say, if you take, so how big is 10 to the minus 21, right? If you take the distance from the Earth to the sun, it's 150 million kilometers. If you distort that distance by 1 part in 10 to the 21, it's about the size of an atom. Right? So that's kind of what we're doing, right? We're measuring a distance like that. It's just, we're watching it wiggle just a little bit, right? And we can measure that actually with pretty good signal to noise. So the way we do it, So with one of these laser interferometers, I'll show you how this works. Here's our laser, here's our beam splitter, and here are two mirrors. You shine a beam out of your laser, it splits the beam splitter, goes to the two mirrors, comes back, and as the two mirrors change, the light coming onto your detector here changes as well. And the way this works, you can imagine this light is an electromagnetic wave. The yellow is the intensity of the electric field. It's bouncing off the arm. The blue is the electric field from this arm. They come back together at the beam splitter, and they combine here. Now, you can see every time there's a plus on the yellow field, there's a minus on the blue field. And so they add up to be 0. So there's no power until you start to distort those arms. And then the field coming out of this port of the beam splitter, the electric fields change, and the changes in those electric fields as they line up and go out of alignment cause power at your detector right here. What this means is you're measuring, in our case, this 4 kilometer, this 2.5 mile long, this 4 kilometer arm with a ruler, and the ticks on that ruler are a wavelength long, right? So they're about, in our case, about a micron. So it makes a really good ruler. And not only that, but it's not really good enough, right? In fact, what we do is then we measure this intensity very carefully, and we can watch even very slight changes in that intensity. So we can actually measure I should have done this earlier, a trillionth of a change in that wavelength. All right, so a little bit of a digression on history. Turns out this has there's a funny little connection in history through here. So this is the Michelson interferometer, built in 1887 by Professors Michelson and Morley. And it looks a lot like what I just showed you. There's a light source here. They used an oil lamp. There's a beam splitter. One of the beams goes through the beam splitter, bounces back and forth a whole bunch of times, gets to E, bounces all the way back to the beam splitter. The other light bounces off here, bounces back and forth to E prime, back to the beam splitter. Those two beams recombine and come to a little sighting glass here at F. They did this because they were trying to measure the luminiferous ether. In the late 1880s, the whole electromagnetic theory was just getting started, and waves travel through something, right? We all know this, at least we think we do. Sound travels through air, water waves travel through the water, light must travel through something. And they called that something the luminiferous ether, and these guys were looking for it. And they had a very clever experiment. What they figured was that as the Earth was moving along through the ether, one arm was going straight into the ether and one was sideways. Now this arm, as you go in, as the light goes this way, the arm's a little shorter, a little longer. When the arm goes back this way, it's a little shorter. There's no net effect for this one. But for this arm, as you go along, the light's got to go not only to the end of the arm and back, but also has to travel forward a little bit. So this light has to travel a little farther than that light. And interferometers are really good at measuring lengths. So Michelson and Morley said, hey, we should be able to measure the Earth traveling through this luminiferous ether. Not only that, but they did a really clever thing. They took this 5 by 5 foot chunk of rock, and they were able to turn it, right? So they start going this way, and then as they run along, so now my left arm is going to look a little longer. They're going to rotate this block. Now my right arm is a little longer, and now my left arm is a little longer, and now I better stop or I'm going to crash into something. So they did this really pretty measurement. This particularly appeals to me. If you look at the paper, what you'll see is they say, this is version 2 of the experiment. In the first experiment, one of the principal difficulties encountered was that of revolving the apparatus without producing distortion. And another was its extreme sensitiveness to vibration. This is still true. It was so great that it was impossible to see the interference fringes except at brief periods when working in the city, even at 2 o'clock in the morning. And as a graduate student, this really appealed to me. They did a clever thing. So that chunk of rock is actually sitting in a pool of mercury. Right? This is like science in the old days, right? And you can just turn that thing evidently very nicely. And they didn't see anything. They didn't see a darn thing. So here's their measurement, right? And here's their prediction. for what they should see. Actually, they divided the prediction by 8 so it would fit on the same plot. And they're like, that's weird because if your interferometer is stationary, it's clear that the arm should be the same length. But if your interferometer is moving, then the arms should seem like they're a different length as you go through the luminiferous ether. And this caused quite a bit of discussion in the physics community at this time. And no one could explain what was going on until Albert Einstein came along in 1905 with his special theory of relativity and said, look, the speed of light is a constant. It doesn't matter whether you're sitting still or you're moving along at a constant velocity. The speed of light is the same. Right? There is no luminiferous ether. That's why you couldn't measure it. The special theory of relativity then evolved into the general theory of relativity, which predicted gravitational waves, which we measured 100 years later with a Michelson interferometer. I just think that's cool. All right, so here we come back to our interferometer. It's hard to measure these distortions in space-time because space doesn't like to get stretched. What are some tricks we do to make this machine actually good enough to do it? There's sort of 3 classes of tricks. First, you make the arms really long. Our arms are 4 kilometers long, 2.5 miles long. That's how much vacuum system we could afford. That's how long we made it. The longer you make the arms, the more absolute length change you get for a particular strain. So the longer they are, the easier it is to measure your strain. Second thing you do, here's a little more detailed version of the interferometer. The second thing you do is you measure the distance change in those arms very accurately. So somehow you have to measure this length and measure this length very precisely. I'll tell you just a couple of tricks that we do to make this happen. First, like Michelson and Morley did, we bounce the light back and forth in this 4-kilometer long arm about 300 times. So instead of being sort of like 4 kilometers, it's really like, 1.2 thousand kilometers. So it's the effective length is much, much longer. I'll just point out right now there's 100 kilowatts of optical power in these arms. By the time we're done, it's going to be almost a megawatt of power stored in these arms. Why do you need that much power? So when the light comes back out of these arms, it comes to the beam splitter, and your ability to measure the relative change of those 2 arms comes down to the counting statistics of the photons at that beam splitter. If that's true, what you want is a lot of photons. So another trick we do is we have a really big laser. We have the best various ways to define best. For my way, we have the best laser in the world. So this thing can put out about 125 watts of very, very, very clean laser light at 1 micron. It's a gift in kind by the German government. Here you can see a couple of guys at Laser Zentrum Hanover working on that laser. It can put out about 125 watts when it's working. But that's not enough. Right? We need more power than that. So there's another trick we play, and I'm just going to kind of tell you what it is rather than trying to describe it very carefully. In the picture you saw of the interferometer before, what you saw is that when there's no gravitational wave, there was almost no light coming onto the detector down here. Almost all of the light was going back towards the laser. So what we do is we build an optical cavity, and sort of in a very California sort of way, we recycle that light. Instead of just letting it fall out of the interferometer, we turn around, we push it back in. And we store this light at our beam splitter. So with our last run, we had 20 watts going into the interferometer. We had 800 watts in our power recycling cavity. Sorry, I love acronyms. In our power recycling cavity at the beam splitter. And that gave us enough optical power that you could really accurately measure where you were on that optical fringe. The third thing we do, this is my favorite. You keep the mirrors from moving, right? The interferometer tells you how far apart the mirrors are. So you want to measure that very accurately, and you want to keep the mirrors from moving, right? So the only thing that changes the distance is the gravitational wave actually stretching the space. So how do we keep these mirrors from moving? Here's a picture of the vacuum system that holds all these things. It's a big ultra-high vacuum. That mirror that I showed you before is in this vacuum chamber right here. And if you zoom in and sort of cut away the walls, what you see is a contraption that looks like this. For scale, These posts are about 8 feet tall. The top of this chamber, which has been taken off, about 18 feet off the ground. Here's our mirror. We start measuring above 10 hertz. So at low frequencies, these kind of distortions, we just try to control those out. We only start looking for fluctuations in space faster than 10 cycles a second. And we look for it at these mirrors. At 10 cycles a second, at 10 hertz, this mirror has to be moving 1 billion times less than the ground does if we want to hit our requirements, which we're doing a pretty good job of. We do that with 7 stages, 4 stages of pendulum, 2 stages of seismic isolation system, and an external stage of laminar flow hydraulics. I'm just going to tell you about the hydraulics for just a second. There are lots of things that make running an interferometer like this difficult. One of them is that you have to keep the distance of those arms more or less fixed. It can't move by more than about 10 to the minus 13 meters, or the light comes out and the whole interferometer stops working. So to hold it at its operating point, you have to control the RMS length of those arms. Now, we all know about the tides. Right? The moon goes overhead, the water goes up and down. What most people don't realize is that, in fact, the ground moves up and down too, about plus minus 6 inches. And as that tidal bulge goes past the Earth, the ground around that bulge gets stretched a little bit. And these 4-kilometer arms actually change their length by plus minus 120 microns twice a day. Now, the distance between the mirrors has to be fixed, and the ground is sliding back and forth underneath them. So you've got these big hydraulic systems that push the mirror against the ground as the moon is distorting the ground, so you can keep your interferometer working. The guy who told me about building hydraulics like this, these super quiet laminar flow hydraulics, is Professor Dan DeBray, who's sitting right here. So he's kind of the smart guy in our lab. If you have any questions about seismic, talk to Dan. He knows all about it. All right, so back inside. So here are mirrors. Here's sort of a CAD drawing of the mirror. The mirror itself is a piece of glass about 34 centimeters in diameter, about 20 centimeters thick, weighs about 40 kilograms, about 90 pounds. And it's suspended as a 4-stage pendulum. And I brought a demo. So why would you suspend? So here's the advanced LIGO optic. Why would you suspend this on a pendulum? If you take your suspension point and you move it at low frequencies, of course your optic kind of follows along. You can use this to put your optic where you need it to be for the interferometer to work. If you move your suspension point at the resonance of the optic moves a lot more than your suspension point, and this is bad. So we have all kinds of controls around our optic to damp out those fundamental modes. The good thing about a suspension is that if you move the suspension point at high frequencies, what you see is you get a lot of attenuation between the suspension point and the optic. Works both horizontally and vertically. And of course, if some is good, then more is better, right? See if I can do this. So with a 2-stage pendulum, you should be able to move the top really kind of a lot. And you can see now my suspension point is moving a tremendous amount. And as long as I don't hit the resonance, the optic just can't keep up. So you get a lot of isolation between this top of the optic and the mirror itself. So for advanced LIGO, it's a factor of about 10 million at 10 hertz. We have the world's best optical coatings. And if we do it right, the motion at 10 hertz for that optic is actually driven by its thermally driven excitations. So the ground isn't actually the driving anymore. It's the thermal fluctuations of that optic. And one of the cool things that we do to make that happen is that, in fact, not only is this thing a piece of glass, but the one above it is a piece of glass, and they're bonded together. They're little ears that we join onto here. And then onto the ears, we have glass fibers. And this whole thing is welded together into a single, when you're done, it's a single piece of glass. If you whacked that thing, you get in a lot of trouble. But if you whacked it, it rings for about 10 million cycles before it finally calms down. Here's a picture of the scale of it. This is Betsy. She's our lead suspensions expert at the Hanford site, standing next to one of the engineering prototypes. Here's a mock-up of the mirror. You can see how big this thing is, right? Here's the top of that 4-stage pendulum attached to the optics table. If you look at the real optics, what you see is something like this. They're much prettier, but you can't actually see who's working on them. So that suspension actually gets attached to the seismic isolation table. This is the table here. Suspension bolts up on the bottom. At 1 hertz, this table is 1,000 times quieter than the ground at 1 hertz. And this is really useful because, for instance, at the Livingston site, there's a train that's right near one of the end stations, right? So the end mirror of one of the arms, there's a train next to it, and they load logs up onto the train, and they drive it across this rattly bridge. And it used to be that twice a day, the whole interferometer would fall out of its working point, and you couldn't run it while the train was going past. Now, smooth as silk, because the table here keeps the thing quiet at low frequencies, so it's easy to control. You can see it's got springs here and masses, so you get the same kind of pendulum isolation that you do with your suspension. But also it's covered with high-performance sensors and actuators and control systems. And so at very low frequencies, we can use our active control systems to hold it quiet. Again, Dan told me how to do that. Here's a picture of it being installed at the observatory. And a couple of pictures of the prototypes down in my lab, down on campus. The 2-stage platform here, the optics table is on top. This is Wencheng Hua. Here's Dan Clark next to a later version where it's got all kind of high-performance sensors set around on it. These are for control. These are to measure how well the thing does. As I said, at 1 hertz, we can make it 1,000 times quieter than the ground does. OK, so now we've done sort of 3 things. We've got really long arms. We can measure the distance between the mirrors in those arms very accurately. And we're holding the mirrors really quiet. And what we're looking for is for something to change the length of the arms. And for that something to not be us, right? So this is it's called a spectrogram of the 2 events. We've got about ½ a second of data. And what you can see right here is the event. This is going to be a sound. I'm going to play this in just a second. Let me tell you what's going to happen. For the first sort of ½ a second, there's going to be a rumbling. And that's what the interferometer sounds like when there's no signal. It's just sort of the residual noise in the instrument. And then the signal comes in. You can see it's about 200 milliseconds. And here we have 30 hertz. And you can see it's very loud, starting at 30 hertz and running up to about 150 hertz over, not quite 200 milliseconds. So here's what it sounds like, I hope, with just the noise. So that's no signal. Let's see if I can do that again. Now, we're going to play it again. I'll play it twice with the signal, and then we're going to shift it up to kind of put it a little more in the audio band. Same signal, just frequency shifted up a couple hundred hertz. Play it twice at the higher frequency, and then we'll repeat that. So this is what it sounds like if you take the output of our detector and you play it on a pair of speakers, right? So they told me I had to make the title something about the sound of black holes colliding. This is it. The little whoop, whoop is something we've been looking for a long time now. We call that the chirp. And when you take a look at the signal as a function of time, here you can see it at Hanford in Louisiana. Again, it's sort of ½ a second long. The strain, the maximum strain, is about 1 part in 10 to the 21. And this is the Hanford and the Louisiana detectors lined up. Here we have the best fit numerical relativity model of the event. And when you take the actual signal and you subtract the best numerical fit for the signal, this is what you get left. This is the noise. So we call this our signal, and this is our noise. And here's a spectrogram of that. This signal is filtered out, so you don't really see anything below about 40 hertz. If you do a better model for what that signal looks like down to low frequencies, you get a signal that looks like this. And I should really, at this point, give a shout out to all the people doing numerical relativity. 10 years ago, you couldn't actually model a single orbit of two black holes going around each other on the computers. You just couldn't do it. I was at a talk once, and someone said something like, the coordinate system for the calculation fell into the event horizon. You're like, I'm not even sure I understand what that means, right? But it's, as Bob Wagner down on campus said, it's like, well, wasn't a very good choice of a coordinate system. Now, was it? Anyway, you can see they've gotten much, much better, and it's critical to actually being able to understand what happened. So from this waveform, we think the two black holes were 29 and 36 solar masses. And my wife was harassing me earlier this week, saying, the biggest, like the question that people always ask her is, how do you know what the black hole masses were? So let me just give you a comparison. This is the signal that is the best fit to the signal that we saw, about 200 milliseconds. Here's a 4-second version of the signal that we were expecting. This is two neutron stars. Neutron stars are about 1.4 solar masses. Here it's about 50 hertz, here it's about 900 hertz, and you can't even see what's going on in here because there's so many cycles. If you zoom in on the end, then you can do a better job of comparing these two signals. And what you see, so here for the same 200 milliseconds at the end of the signal, this is what a black hole in spiral looks like. This is what a neutron star in spiral looks like. They look they look qualitatively very similar. The frequency is getting faster, the amplitude is getting bigger, and then it falls off. And that's true for both of these. But the actual frequencies are very different, right? And it's the change in frequencies that lets you measure the mass. Another thing you could do is you can compare when these two signals are at about 65 hertz, right, sort of right here. So this is what the neutron stars look like, the lighter masses at around 65 hertz. You go forward 5 cycles, looks about the same. Go backward 5 cycles, looks about the same. If you squint, you can see that the amplitude here and the amplitude here has changed a little bit. You know, here if you start at 65 hertz and you go forward 5 cycles, the whole event's over. You go back in time 5 cycles and you're not even in the detector band anymore. So by looking at the rate of change of that signal, you can figure out what the masses are. We think those two masses were 29 and 36 solar masses, and they've spun into a single black hole which was 62 solar masses. And the 8th graders in the room are probably doing some math right now. What they see is that this is 65 and this is 62, and that as these two black holes crashed into each other, 3 solar masses of mass went away. So Einstein tells us that E equals mc squared. M is 3 times the mass of the sun. This thing emitted 3 solar masses of energy in a few milliseconds. That means there was a much power coming out of this thing. The amount of power coming out of this was 50 times more than all of the power of all of the light coming off of all of the stars in the visible universe. I can't even get my head around that, right? It's just ridiculous, right? It's a tremendous amount of energy. And yet, when it got to us, you could barely see it, right? I mean, it's just, the signal noise is pretty good, but strain of 10 to the minus 21, not very much. We were lucky that we saw it, in fact. How lucky were we? The first observing run for Advanced LIGO was supposed to start on Friday, September 18th. For about a month before then, we've been doing an engineering run, kind of getting everything ready for the first run, getting it all tuned up, making sure it ran for a long time without trouble, making sure all the calibrations were right. In the middle of the night on Monday, people are like, okay, it's time to go home. Switch it to on. They leave the site. It's like 2 in the morning at Hanford. About 45 minutes later, after everyone's left, signal comes in. Like, well, I guess we're starting the observing run a little early, aren't we? Don't touch it. Don't touch the machine. We've got to get enough statistics that we can tell if this is real or not. All right, so I'm coming near the end of my time. We spent a long time getting to the point where we finally measured the first gravitational wave. And so you might say that we've gotten to the end of our quest. But I'd like to argue it's not the end, it's actually the beginning, right? It's not the end of the quest to find gravitational waves. It's the beginning of a new kind of astronomy. You know, people have been looking up at the stars for ever since there were people. Like you walk outside tonight, and if it's not too cloudy, you can walk up and see a beautiful night sky. The neat thing about looking at the stars in the modern era is that when you look in the visible light, you see images like this of our Milky Way. But every time you look up at the stars with a new instrument, what you see is something different, right? Here's what our Milky Way looks like if you look at it with the Fermi telescope run here out of SLAC. This is what the sky looks like in gamma rays. And you can see that there's the Milky Way in here, but it is not the same. The first gamma ray telescope that went up, they put it up to watch the Russians to make sure they weren't setting off nuclear weapons. And what they saw was that there were explosions in gamma rays coming from the other direction. And they thought, maybe the Russians are setting off nuclear weapons on the other side of the moon, right? Which is pretty crazy, but in fact, what's actually happening is probably even more crazy. And we're not exactly sure what it was, but maybe I'll come back to that in a minute. Here's what the sky looks like if you look in the infrared. This is a satellite image from COBE, from the FIRAS machine. Here you can see now the center of the galaxy is very bright. Here it's very dim because it's obscured by dust in our galaxy. Here you can see it quite clearly. If you look at that same telescope, same instrument, same satellite, and instead of looking at the infrared, you look at the microwaves, and you pull out the galaxy, and you look at the stuff that's behind the galaxy, what you see are fluctuations in the microwave field that are left over from the Big Bang. That's what COBE tells you. These are fluctuations in the microwave background left over from the Big Bang that tells us how the universe started. And now we have another way of looking at the sky, and it looks kind of like that. Actually, to be fair, this thing was only on for 200 milliseconds, so I should turn the star off right now, but I just can't bear to. But we think that now with this new instrument, we're going to be able to learn a lot more. With gravitational waves, you can look at anything that's got a lot of mass and it's shaking around. This might be the centers of supernovas, when the center of that star collapses, driving one of the most energetic events in the universe. It might be the neutron star that's formed after this supernova. The neutron star here, this is the Crab Nebula. In 1054, this was a supernova. The Chinese could see it in the daytime and wrote about it. Now there's a neutron star in the middle. It's sort of the density of nuclear matter, and it's spinning around 60 hertz. If it's got a little wart on it, that little wart's spinning around 60 times a second. And pretty soon, the gravitational waves from that thing, maybe we'll be able to see them. Be very interesting to tell you maybe what the neutron star is actually really like. Maybe when you have two neutron stars that crash into each other, the kind of thing that LIGO started out looking for. Here's our little neutron star in spiral from earlier. What you see when these two neutron stars crash into each other, these are actually matter, right? They're not like curvature of space-time black hole things. They're actually stuff. And when they crash into each other with their dense matter and their magnetic fields, what you'll probably get is a huge burst of gamma rays. We think that's one of the sources of gamma ray bursts. If we see a gravitational wave signal like this, followed by a gamma ray burst on, for instance, the Fermi telescope, a few milliseconds later, we'll know what gamma ray bursts come from. It'll be very exciting. Not only can we combine the gravitational waves with other kind of instruments, but there are also a bunch of new gravitational wave instruments coming online. LIGO can see gravitational waves at around 100 hertz, 100 cycles a second. But there's some other instruments that people are working on. There's one in outer space called ELISA. Instead of being 4 kilometers long, those arms could be a few million kilometers long, and look for gravitational waves at lower frequencies down here where you might have black holes in the center of the galaxies crashing into each other. There's also a group called Nanograv, the people I stole this slide from, looking at radio pulsars around the galaxy and looking for distances from us to the radio pulsars to change at sort of periods of weeks or months, indicating that very low frequency gravitational waves have gone by from, for instance, again, the black holes in the center of galaxies crashing into each other. There's also people looking at the microwave background, that thing that I showed you before with Kobe, looking for fluctuations in that microwave background caused by gravitational waves from the beginning of the universe. So I'll argue that it's not the end, it's actually the beginning of a new kind of astronomy. And I'll also argue that although it's the end of my talk, it is the beginning of the time for you all to ask questions. I'm really glad you guys came out. Thank you very much. Now I think...
Okay, so Brian, thank you very much. We now have time for questions. And let me remind you of how this works. There are some of my colleagues standing in the aisles here with microphones. Raise your hand and be recognized. Wait until you get the microphone to ask the questions. Otherwise, we're recording this. The question will not be in the recording. And sir, why don't you take the first question?
You have this wonderful instrument. Has it measured anything else since?
Good question. This event was from data from the first third of the first observing run. The second two-thirds of that observing run, we're now processing the data. And those that will release that soon, in the next couple of weeks, maybe a month or so. And then we'll know. Still looking. Then we're going to start the second observing run this fall. And the predictions for that are anywhere from a few events to maybe 10 if we're super lucky. We'll have to keep your fingers crossed for us when that run starts. But yeah, check the news in a couple of weeks and see if the data from the rest of the first observing run has come out yet.
I have the same question.
Anyone, please.
The hope of matching your measurements of gravitational waves with the gamma burst related to the same event. And the
I'm having trouble understanding what you're saying.
So that collision of these two black holes probably will also produce some burst of gamma rays.
Maybe.
Any hope of matching, like time-wise, and confirming that was, and maybe finding the place
so
in the...
Is there any kind of coincident thing that we saw with other observatories that went along with this gravitational wave? For the neutron stars, you should definitely see something like that, because there's real matter, and it's crashing into each other at some reasonable fraction of the speed of light. You would definitely expect to see gamma rays. For the black holes, if the black holes have kind of sucked up all of the normal matter around them, you wouldn't expect to see any signals in the visible, because there's just space-time getting distorted. If there's still some matter around, then you might see something. And in fact, the Fermi collaboration released a paper recently saying that there might have been something in the gamma rays about 400 milliseconds after the event. It wasn't strong enough to be significant except for the coincidence time, and it was kind of right at the edge of the Earth, so it's subject to confusion, but it's one of these things that you can't dismiss it. So I'll give you a maybe on that one.
And also that would be a way to compare the speed of gravitational waves.
It would be.
Yeah,
it would be a way to see if they're actually traveling pretty close to the speed of light, which would be very interesting to see. I mean, we expect that they travel at the speed of light, but being an experimentalist, I'd like to measure it, yeah.
There's a question here.
That last question kind of was my first question, so I guess I'll move on. I'm kind of curious, going back to Michelson-Morley, they didn't have a laser, right? How did they pull that off?
They were good. They had an oil lamp. Yeah. Yeah, they had a, so there's a thing called the coherence length, which tells you when light comes off of something, how far along can you go on that light, and the wavelengths to still be sort of reasonably well related to each other. For LIGO, it's like forever. For these guys, it's very, very short. And they had to align the absolute length of their 11-meter long arms to just a few, I don't know, just a few wavelengths to get their oil lamp fringes to line back up. They were very patient.
I've been texting my grandson notes from this lecture, and his question is, can anything surf a gravitational wave?
Oh. I wish. Wouldn't that be cool? Amplitude's pretty small. And people have talked a long time about trying to somehow harvest the energy of the gravitational wave to some good effect. And so far, we haven't done it yet, but you know, he's still young enough, he might be able to, in a few years, he might be able to tell us the answer. That'd be good.
Okay, please.
Thank you. How long did it take to build the entire structure?
Yeah, so we started, so initial LIGO got its funding in the mid-90s. Built the initial LIGO detector, kind of the construction of that happened in the late 90s. Ran that for a number of years. Didn't ever see any signals with that. I started doing research on the advanced LIGO detector when I got here to Stanford in 1998. Started working with Dan and others to figure out how to build those seismic isolation systems and doing sort of the research for those. We started installing in like 2009, I think, about. And the machine was down for several years as we were bolting stuff into it. So it's been a while coming. Yeah.
Okay, way in the back.
Yeah. Do gravity waves distort other things besides length, such as I'm thinking time? And if so, do you have to compensate for that when you do your measurements?
Right. If you remember the animation at the beginning, there were some funny color distortions near the black holes as they were colliding, which meant that there was some time distortion. The color was the time. Right? There was some time distortion near those black holes. By the time the waves get to us, they're weak enough that you can describe the event as merely a distortion of space. You don't need to involve a time distortion as well. So I'll stop there. I'm not a GR guy, so I'll just stop at that. It's hard to think about these things.
Okay, my question is, I understand that you're measuring about 10 to the minus 21 meters. And you mentioned earlier that you were able to measure about 1 trillionth of a wavelength. But a wavelength is only about a micrometer. So that doesn't get you anywhere near 10 to the minus 21.
Right.
So how do you get there?
Yeah, that's right. So we're measuring a strain of 10 to the minus 21. The length is 4 kilometers. So the distance we're measuring is 4,000 times 10 to the minus 21. It's about 4 10 to the minus 18 meters is the length that we're measuring. And that's where that extra factor comes from. Right? So that's how we're getting the factor of 10 to the minus 12 of 10 to the minus 6 gives you 10 to the minus 18 meters, and the signal is about 4 10 to the minus 18 meters.
Yeah. Let's see. I wondered if you had any theoretical estimate for how often you have colliding black holes. Like, how lucky were you you have to wait another century for another one like this?
I should have said this when I was giving the talk. In the history of astronomy, there's only ever been one collision of black holes ever measured. And that's the one that we did, right? So, I mean, so far, right? There might have been a second one in the first set of data that's kind of marginal. Anyway, there's more data coming out soon. Based on 16 days of data and one event, you can make some statistics about how often these things happen. And any statistics teacher would tell you that it's kind of dodgy. We think it's between 2 and 400 black hole binary mergers per year per cubic gigaparsec. 3 billion, for cubic 3 billion light years. We hope soon to get a better estimate on that. It's, and it's funny, it's a guy named Franz Pretorius, who's actually the guy who got that black hole merger calculation to work, was out at Stanford a couple of months ago giving a talk, and he's like, how come everyone's like dissing on these black holes? I love black holes. Like, why weren't you thinking about them? And there were a few people who thought we'd see them first. Kip Thorne, for instance, was one of the guys who said, you're probably going to see black holes first because the signals are so big. But the problem is we had no idea. We had no idea what the event rate was. There are several papers that predicted it correctly and a whole slew of papers that predicted it incorrectly. So we're actually very pleased to actually have some data now. Yeah.
Is somebody over here?
I was wondering if all the energy that was released by the two black holes colliding was in the form of gravitational waves. You said the mass shrank by about 3 solar units.
About 3 solar masses. That we think so. Yeah, we think that it all came out as gravitational waves. I mean, that's what the numerical relativity models show us. If you believe general relativity is right, then the answer is yes. We'll see. Right?
So could the gravitational waves, if something in space is close enough to the black holes colliding, could it cause like a physical change in the object, like pushing it off orbit or like breaking off a chunk of it?
Yeah, it would be bad if you were too close to those gravitational, to those two black holes spinning into each other. What you would see, most likely, if you got really close, is you wouldn't see the wave at first. What you would just see is the force of gravity being really strong on you, which would kind of cause, you know how the moon causes tides on the Earth, and it stretches the Earth just a little bit? It would be like that, except it would be a lot worse. It would like stretch you right out into a pencil. And that'd be it for you, and you kind of wobble around as the masses went past. Yeah, it'd be ugly.
Okay. Back there.
I was the age-old.
Who's asking? Where are you?
Right here.
Ah, okay.
The age-old question: have we figured out whether gravity is a wave or a particle or both?
So in this regime, we're treating it purely as a wave. You would, in a place like SLAC, which is filled with particle theorists, right, particle physicists, you better say something about the graviton. The mass of the graviton is very small. It would be surprising if we could build something that could individually measure gravitons. There's a very interesting paper, though. I'm looking for a whiteboard. If you go to papers.ligo.org, papers.ligo.org, you can get the main event, the paper describing the event there for free. You can download it for free. There's also a whole series of companion papers. And one of them talks about what you can learn about general relativity from this event. And although you can't see individual gravitons, what you might think is that if gravitons had a mass, that they might get smeared out they wouldn't be traveling at quite the speed of light. And if they're not traveling at quite the speed of light, then maybe the more energetic ones would travel at a different rate than the less energetic ones. And that waveform, which has some low energy ones at the beginning and some high energy ones at the end, would get distorted as it traveled 1.3 billion light years through space. And from that, you can set some limits on sort of the behavior of the graviton. So far, we don't see anything interesting. But it's an interesting question to ask. And I think as we get more statistics and look at things that are farther from the Earth, maybe we can start to accumulate some more data about sort of the behavior of the graviton. It'd be interesting to see.
What about the velocity of propagation of gravitational waves? Is it equal to the velocity of light or?
Oh, the speed of the gravitational waves. Is it the same as the speed of light?
Waves.
We think so. We don't have a good independent measure of that because all we have is these sort of 8 cycles in 200 milliseconds. That's what we got. You can predict the generation of that signal very accurately with a numerical relativity model, even when the gravitational fields are very intense. And you can see in here, space is quite distorted, and we can still do a good job of measuring that, which means that numerical relativity, general relativity seems to be holding up to the tests. And if that's true, the gravitational waves should be traveling at the speed of light. Now that's a lot of wherefores and what-fores and maybe this and maybe that. We don't have any evidence, but I will say this, we don't have any evidence that they're not traveling at the speed of light. There was a question earlier if there's some other thing like a supernova that emitted neutrinos and light, then you could compare the time that the light gets to you and the time that the gravitational wave gets to you and get a better measurement. We haven't been able to do that yet, but it would be interesting to see that.
Thank you, sir.
Do you have any thoughts as to whether the experiment that you have there can shed some light on different theories of quantum gravity? Is it sensitive enough to discriminate between different theories?
I don't think so. Again, I'm trying to think if I've seen any discussions about gravity with interesting potentials, Yukawa potentials and that sort of thing that you could dismiss with this. And so far, I think that would be a tough one. That'd be a tough one. Or maybe you want to chime in on this?
Yeah, I'd like to chime in. There have been some papers on the question of how these 30 solar mass black holes got that close together so that they could actually make this event happen. And some of the theories of that have to do with quantum gravity in the early universe. So that's a way at it. Other people think that, well, there are lots of binary stars and some of them are big, and this is just something that would naturally happen. And it's hard to get data on this. How many black holes do you create that are a certain distance apart and in what kind of environment? So I think astrophysicists will be arguing about this for a long time. But potentially this is a source of information if we could only ever figure it out. Okay. Let's take 3 more questions and then we'll end. So please, who is that? There's one over here.
Hi. So I know in, I think, 2014 or 15, I think there was a false detection of gravitational waves by LIGO that had to deal with like these E modes and B modes, and it was, I think, talking about primordial gravitational waves. And
that wasn't LIGO. That was the BICEP experiment.
Oh, it's from the BICEP. Okay.
So also here at Stanford, yeah. But yeah, the primordial stuff is not LIGO. We can't see down to those kind of frequencies.
So, since if those were a false reading and those were, I think, connecting to the theory of the Big Bang, since we've detected these gravitational waves from these black holes, does that mean does that mean that the search for these primordial gravitational waves is going to continue still, or is this good enough to I guess, confirmed?
No, I think that the questions that we're trying to answer with black holes and neutron stars and sort of more contemporary astrophysics, in the last few billion years, I think are quite complementary to the early universe questions. The things that Bicep and Planck and the primordial black gravitational wave people are looking for, so the imprint of gravitational waves on the microwave background, tell us much more about sort of things that were going on right at the Big Bang. And I think that both are interesting and they're different. If anything, hopefully the sort of the excitement that comes from this will, drive the field forward a little bit. That's what I would hope. I'm not supposed to be answering questions.
You twice described time-space, or space-time, excuse me, as stiff.
Yes.
Is that more correct than saying that these forces are weak, or was it an arbitrary choice?
It's a similar way of saying the same thing, right? I mean, it's just, except that when you talk about two objects close to each other, and you say, well, you look at the electron and the proton, and they've got some electrical force, and they've got some gravitational force, right? You don't need a wave to describe the gravitational force between them. You can just say that, the electromagnetic force is much, much bigger than the gravitational force. But by the time you get out to where you're looking at, several wavelengths away, the sort of classical way of describing gravity is just a force. You can't really use it anymore. And so you need sort of Einstein's way of describing space-time. And there you sort of have to rely on things like saying space-time is very stiff, right? Because it talks about how the waves are propagating. But yeah, in the end, it better come out to the same thing, right?
Yes. Okay, last question. Who has it?
There's one here. Oh, yes.
Before we close, is it possible to hear the sound of black holes colliding one more time?
One more time?
I'm sorry, we couldn't hear you. Put the microphone closer to your face and repeat the question.
She was hoping to hear the sound one more time. Let's see.
Okay, there it is. Thank you very much. Okay, and thank you all for coming. We'll go out in the lobby, and Brian will be out there